Today we are talking about Gauss's law. Okay, this is probably the most confusing section in all of Physics C. Okay, so let's talk about it, but I like to do a quick review of the electric field at a point charge, infinitely long wire, and infinitely large plane. Okay, we did this one somewhat last time, but it's a good review, so let's do it. Here, electric field, if there is a point charge with a whatever the charge quantity Q positive, then the electric field is given by K Q over R squared, R being the distance, right? Now, conceptually, why is it like that? I think we talked about it last time, but we'll talk about it again. So imagine there is some kind of a window that this electric field lines, we call flux lines, go through like that, like that, and like that, and oh. You know what I'm saying? So what happens if I double the distance? If I double all distance, about that looks about like double. What we have done from symmetry is that we have quadrupled the area. Remember the scale factor from geometry? Now, I only drawn 4 lines here, but electric field lines may or may not exist. We are only visualizing this. So imagine this field density, these lines are called flux. Whatever penetrates the flux lines, that this square will penetrate these 4 squares, correct? And the density of these lines is what we measure as the strength of the field, so that this field has to be proportional to distance squared. You know what I'm saying? And then, of course, it has to be proportional to the amount of charge. So we pick this up. So this is a natural phenomenon, not only true for electric field, but any kind of a point source, such as gravity and anything like that. It's just a matter of the direction. So we have that. Now we're going to compute the electric field of infinitely long wire. Say we have positively charged long wire. Say that looks like infinity to you. Okay. Of course, no wire is infinitely long, but the key is if you're close enough, then it'll look like infinity to you, right? So, and then even if this wire is really long, if you're far enough away, it still looks like a point charge. So we can simulate many cases with these 3 type, okay? So infinitely long wire, I'm gonna draw, let's say this is the x-axis. About here. Let's put it down a little bit. Not there. Microsoft. Okay. And then at point x units away from it, let's say this distance is x. Good. Now we have to introduce a concept of charge density now. Okay. So I'm going to say charge density lambda is the total charge of the wire over the length of the wire. That makes sense to you? I think you've been thinking like this before. Instead of the volume density, this is called the length density. Of course, total charge on an infinitely long wire is infinity. But in this case, you know what I'm saying, right? Okay. Now let's conceptually think before we start integrating. Same situation as this, but if you have some wire that is straight line would be nicer. If you have a wire that is like this, and then these flux lines will come out, it only disperses like that. And then they are pretty much parallel, up and down. You know what I'm saying? So if you had some kind of window here, let's say that's the size of your window. And then if you double the distance, that looks like double to you, right? That didn't work out. You see, you only double the area because the height remains the same. See, these things will come out pretty much parallel to each other, so it'll disperse. If you're looking at it from the top, it'll disperse in all directions, but from the side, it does not disperse. You know what I'm saying? That way, your electric field has to be proportional to the amount of charge, whatever that is, divided by only R. You know what I'm saying? Because if you double the distance, you're only diluting these flux lines by half, not by fourth. Okay, so we expect this kind of proportionality, except instead of Q, we have to think in terms of lambda. In case this is a finite length wire, and then you want to calculate it, you still want to, whatever the charge, you divide by L, and then you use lambda, which is a lot simpler, less writing, and then later plug this thing back in. Okay, this is a common technique. So think in terms of density. Okay, then we are going to calculate the field. Say we have tiny bit of charge right there, which is dq. Okay, and then we are going to calculate the dE due to this. So this is the direction of the dE. Little tiny bit of electric field that caused by that tiny little segment. You know what I'm saying? Okay. First of all, let's call this distance R and this thing Y. How's that? So we are integrating in terms of Y now because the charged wire, we are adding these things up. Good. Okay, this we can split it into sine and cosine. So this component right here, right? dE cosine theta, and that angle being theta. And then this component right here, which is dE sine theta. Good. Now, since this is an infinitely long wire, for this dq, there has to be at an equal distance away another same amount of charge. And then, if you draw it, you see this y component will cancel out. This thingy cancels this thingy out. And then you just double up in x direction. So we only need to consider this dE cosine theta. Good? Okay. So that's where we are going to start. So dE cosine theta is equal to, well, k dq, right? Over r squared and cosine theta. So far, so good? Okay, then dq, of course, is it our density times dy? So far, so good? Because length times density is the charge in this case. Yes?
Would we be counting 2dE cosine theta?
Okay, we can put 2 here at the now, or we can put it in front of the integral later. Which way do you want to do it? I can do it either way.
Later probably better.
Yeah, because the other one will cancel by the other side, is my thinking. But it's, you see, we are just using that symmetry too, now, either now or later. So we'll do it later. Okay.
It's still r squared when you said that.
No. That's by feeling it, right? If we do this, we're supposed to get something that looks like that, and that's sigma, not that. But we are supposed to get something looking like that. You know what I'm saying? I mean, not sigma, lambda. Okay, so let's see if we really get something looking like that. Good. And then R, let's calculate R. Is our R, wrong color, is R equal to x squared plus y squared? So far so good. So our R here is x squared plus y squared. Good. What is cosine theta? It's x over r, isn't it? So let's put it here. So x over r, which is this. So far, so good. Let's simplify this. So this is same as k lambda x on the numerator and then denominator x squared plus y squared 3/2 power dy. Now we can integrate. Good. Okay. Any questions before I start integrating? Okay, I'm gonna push this thing down now. So my electric field is equal to, instead of negative infinity to infinity, put 0 to infinity, and then we use symmetry that he suggested earlier. Good. So that'll count for the other lower half. And then we put k lambda x over x squared plus y squared 3/2 power and dy. How's that? What kind of trick are we using in this integral now? You all agree with the setup? So we can just concentrate on integral. What's the trick here?
1 over x tangent.
Almost. We're doing tricks up, right? So our y needs to be not 1 over x, but x tangent theta. Do you see it? That way, this expression, x squared plus y squared, 3/2 power, I'll just work it out for the sake of people who are watching this video. So that is x squared plus x squared tangent squared theta 3/2 power. This is slightly confusing, so common factor x, right? And then you have x squared and then secant squared theta 3/2 power. And taking 3/2 power, so you get x cubed, and then you have secant cubed theta. Oh no, secant cubed theta. No. You remember secant cubed theta? Tell me it ain't so. Hopefully this will cancel out. Let's see. And then, not to forget, we need dy, derivative of that thingy. So we have x secant squared. Do you see it's going to be nice? Not, we are not integrating secant cubed theta, okay? So let's make the substitution. So 2k lambda x is constant as well, right? Because we are integrating with respect to y. And then what we have is this thingy over that thingy, correct? So we already have x here. I regret putting x out here. I'm going to put x back in because I have a bunch of x's. So x here, and then I have another x here, and secant. I know you can do this in your head, but for the sake of people who are not used to this, I'm just writing it down. And then over x cubed, and then do you see it? It's going to be extra nice. And then we have to change this limits of integration, substitute 0 into y, and then theta is equal to 0. Substitute infinity into y, and then this becomes pi over 2. How nice, eh? Y'all with me? So what we pick up is just 1 over x, 2k lambda over x being constant. And this is from 0 to pi over 2. Do you see cosine theta? Wow, that worked out nicely. 2 over x, and this is sine theta from 0 to pi over 2, which just gives you 1. 2k lambda over x. You remember the form that we were anticipating? kq over r? X being r, our distance, and I guess 2k lambda. So k is there, so 2 lambda is same as q, your charge. How about that, huh? Any question before I continue? Okay, let this stay there because when we do Gauss's law a little bit later, we can get the same expression infinitely easier way. That's the power of Gauss's law. Okay, let's review this. Infinitely large plane. Remember that the circular disk with the charge last time is that, and we are going to do about the same thing, but we are going to take this limit to infinity. So that didn't work out. Hold on. Why do I even trust this computer that it'll do the right thing, right? Okay, say infinitely big plane. So we have potentially infinitely large plane like this, right? And then we want to have our axis through the center, right? A little more straighter line would be nice. That, and this is x. Once again, same setup. Good? But instead of having 2 points, we want to have now, this whole thing is a DQ. You know what I'm saying? And I think we did this one before, but if for this charge right there, which is going to create field in this direction, but that will counterbalance out by this charge here, which will create in that direction. So we only need to figure out this field. That angle is theta. You know what I'm saying? So it's exact setup as this thing now, isn't it? Right? KQ over R squared cosine theta. You know what I'm saying? Okay. So we figure out dE cosine theta, this cosine component. Good. Is equal to K and then our dQ, whatever that charge in that ring, over R squared, where R is this distance, as before. Good. And then we have cosine theta. With me so far? Okay, now let's figure out everything one by one. What is dq? Well, we have to have a charge density sigma now, right? Sigma is whatever the total charge divided by the total area. In this case, infinitely big area, so we do not, it'll have infinitely large charge, so we don't want to think like that. But in case you have a finite ring, as last time's unit 1's example, then you can actually figure it out and insert and substitute this sigma out later. Good? So this is a charge density, so we K, and this thingy is same as our chapter 7, isn't it? 2 pi, and we'll call this distance y. So 2 pi y, and then that's the circumference of this thing times dy is dq. Correct? Say yes. I'm missing sigma. 2 pi k sigma 2 pi y dy is the all of dq over r squared, once again, is square root of x squared plus y squared. So we have x squared plus y squared here, and cosine theta is exactly the same as before, so we have x over r. Good. Okay, any question? You guys look puzzled. Are we good? Okay, let's clean this up, shall we? So we have 2 pi, let's do it like this. Yeah, 2 pi k sigma and x, y over x squared plus y squared 3 half power dy. How's that? Good? is pretty much the same thing as before, except we have extra y here on the top because it's the ring instead of. So our E then is equal to from 0 to infinity again. And then we just dump this thing in here. So we have 2 pi k sigma x y over x squared plus y squared 3/2 power dy. You with me? Okay, this time it's not tricks up because you see y here and then you see y there. So this time we use u sub. Good. And then du, of course, is 2y dy. Okay, so going down. Let's take constant outside. So we'll have 2 pi k sigma x is constant. And then put this, so we have to have factor of half, right? On this u sub, so erase that 2. And then we have this thingy, u to the negative 3/2 power and du. With me? Okay, then. So we have pi k sigma x and then u to the negative 1/2 power, therefore negative 2. Forgot to write down the limits of integration, so let's do that. Substitute 0 into y, so you have x squared. And substitute infinity, so it's infinity. Remember last time it was x squared plus y squared. But then, I mean, in a proper integral, you're supposed to take limit as y approaching infinity, but let's just substitute infinity here. Okay, so we have x squared to infinity. Do you see it yet? So we pick up this infinity, you get 0, right? And then cancel that minus sign, so we'll have 2. Okay, and then pi k sigma x, and then 1 over x, say. X squared in here gives you just 1 over x. And they cancel, so we have 2 pi k sigma. As you can see, the excess disappeared. So it's independent. Yes? Because this is physics now. Your physics book substitutes the infinity around, right? You're only not allowed to do this in math class and AP exam. But in physicists do this all the time. Okay, proper way is limit in front and y approaching infinity. You know what I'm saying? I'm pretty sure it's okay because textbooks do this all the time. Or you can just put limit in front and make it, remember that example from last time, this disk was not infinitely big. It was just finite radius. So just get that and take the limit as that radius approaching infinity. Then you get exactly this answer. But remarkable, because if you think about it, when you have an infinitely large sheet, if you're close enough, such as sun, that's why sunlight comes to us at parallel, right? In this situation, there's no dispersion, so whatever the amount of flux density, flux lines that you catch, if you back up, you catch exactly the same amount. So this is expected to be constant, right? Okay, so those three are nice review and very, very important concept, and we'll calculate all of these using Gauss's law again. Okay, so let's talk about Gauss's law. Idea is, so far all these flux thingy that we drew is pretty much perpendicular, right? But say there is this situation. Same amount of flux, electric field lines are penetrating these two surfaces. And they're exactly the same amount, right? So that this thingy called, well, let's just say flux, right? It's not really this. I mean, you would think this times A is what you like to do. So electric field is more like a density, right? So density times area gives you the total amount of flux. That makes sense to you? But it's really not this, because you see we have to attach cosine theta. Theta being this angle right here. Because it's this, if you make this theta pretty shallow like this, it doesn't matter. It'll only catch the exact same amount of flux because that big area that really doesn't contribute any. So it's really the perpendicular area that contributes. You know what I'm saying? And then comparing in this right triangle, this side is this hypotenuse times cosine theta. And this length is the same. Do you see that? Okay. Do you see a dot product? If you call that a vector. Right? And then, yeah, your physics book will have this expression, E dot dA. What it is really is E dot ds, surface. Those of you in multivariable calculus, you kind of know what it is, right? And if you are analyst, they don't even like this ds vector. So it's d e dot normal vector n, and n being normal to that plane. You know what I'm saying? Then ds. Okay. And then ds, of course, here is a square root of multivariable calculus. Partial f partial x square plus partial f partial y square plus 1 dx dy. Okay, only one of you understand what that means, but without this, does it look like arc lengths? So this is a natural extension to 3D, well, 2D, right? Arc length is a one-dimensional thing, so 2D ds. You know what I'm saying? Okay, we have to make a choice. Do you want to call it dA or ds? Your choice. dA? We'll go with according to physics book. So the total flux, this, right? Oh, dA. So this is d. You know what I'm saying? Say this is dA. Now we integrate this. And we don't know what this surface, I mean, this could be some crazy looking surface. You know what I'm saying? But then total flux, nevertheless, has to be, well, here's a scary symbol. Vector. Thing. Okay, this is not even the really scary thing. And then over the surface, whatever the surface is, in reality, in real multivariable calculus, that flux, total flux, is really double surface integral at S. It's really that. So it's like, yeah, right? What the heck does that even look like, right? Okay. Generally, I mean, we could visualize that kind of surface. Scary, isn't it? Okay, so before we even go there, I have a little sample of what these things look like, okay? We are not doing this by all means, God no, but this is just a note from my multivariable calculus class. Surface integral F is any field, so in our case E, just simple field that looks like this, vector field, ijk. And then this is what's called the paraboloid, and then plane, right? This is one problem. But you can appreciate by just looking at it. Here's a S, and we calculate ds with a cross product. Long story, I know, but still a vector. And then you dot it with a field, dot product. You know what I'm saying? If you take a dot product, then you multiply the x's, y's, and z's and add them up. So it becomes, right, this. And then you take a, in this case, I converted to polar coordinate while I was at it and did it. That's like no problem, right? Of course, it's a big problem. Okay? So whole idea here is if you take the right geometry, you don't have to do any of this. We bypass this mess. But so you know what it is that you're trying to bypass at least. Otherwise, this whole process will make no sense. So let's go back here. Okay? What is this circle? That's even scary, right? It really means enclosed surface. There's a clearly outside and inside, like this. So if you have some kind of surface that looks like this, that's not, we don't put circle around. You know what I'm saying? Because it's umbrella, this bottom is open. You know what I'm saying? So inside and outside is clearly defined. That's when we put this circle around. Okay, then the dot product, right? Dot product is this magnitude cosine theta. The reason this is convenient is our normal vector is typically defined as, this is a normal unit vector. Remember n ds, right? Outward. So if this is coming out, then that angle between the field and our normal vector is acute. Therefore, it counts as a positive count. You know what I'm saying? Okay, E ds dA cosine theta, right? You see, in this case, this is an acute angle. So cosine theta is positive. Where it's going into the field, then it's this situation, isn't it? Normal vector is sticking out backward, and then direction of the field is that, and that's your angle. Picture is right here. This is an obtuse angle. So in this case, this is, so let's write it down. E dot ds dA dA. I keep forgetting. dA is positive in this case, and then E dot dA is negative in this case. Do you see that? And if it's perpendicular, then E dot dA is 0 because cosine 90 is 0, and that's the key. So far, so good. And then the other thing we notice is if there's no net charge in here, no positive, no negative, this is just empty balloon, then whatever goes in must come out to the other side. So total flux count, the way we counted in this integral will give you exactly 0. Do you see that? What goes in must come out to the other side, so they cancel each other. Right? Because we are counting all of this as a negative flux count going in because of this reason. And what's coming out, we are counting it as a positive. So when we count the flux, it's the number of flux penetrating our surface. And then we want to add them all up, which is what this ugly integral right here gives you. Right? Okay, so far, so good. Okay, this was the grand introduction to surface integral and what Gauss's law really is. How do we get away from this type of integral then? By being clever and using geometry. Suppose we have a positive charge in here, okay? And then we have multiple surfaces. First one is spherical with distance, let's say r away, so this is r. Okay, so we have a sphere with a radius r. And then second and third one is some crazy possible shape, which we can figure out the equation and do that, right? Okay, let's just think about this. So if you want to count the total flux, single or double integral? Double, just to make it look like we know what we are doing. You want single integral? Your book uses single integral. I don't know what your packet uses. Did anybody look up? It's really a double integral, but we can use single if you want to. It means still surface integral. Make up your mind now. One, okay, single integral. But those of you in multivariable calculus, it's really double integral, okay? E dot dA, which is really ds, but that's okay. On surface 1, would it be same as through surface 2, and would that be same as same amount through surface 3? Do you guys agree with this assessment? Yes.
I just want to make sure I'm getting this right. Could you say again what flux is?
Flux is the imaginary electric field lines. So when you say E, that's really the field density, right? If you have more of dense flux lines, that means we say strength of our field is greater, right? So whatever this positive charge is generating must penetrate surface 1, surface 2, surface 3. Exactly same count. That's the whole idea.
Like the window thing?
Yeah, it's like window thing, but this is the beauty about this circle integral is it encloses our charge completely. So the total flux count does not change. And that's the key. Yes. dA is, why don't I? Great question.
The small vectors.
dA, say this is a part of the surface, right? Tiny little window, right? It's not necessarily dx dy, but tiny little window, and then with a normal vector sticking out perpendicular, right? This is the A vector, which is really n normal vector, unit vector times ds. Remember last year when you take a cross product of two vectors, and then cross product is this, and this is perpendicular to both of them, and then magnitude is area of this triangle. Parallelogram. So if you just cross the two vectors, then that's our ds or dA. Yes. If you just take a cross product, right?
It's always a perpendicular.
No. When you say area, it's the magnitude of this cross product. That's why mathematicians like this. So you take an area and you stick it, multiply by a unit vector, which is perpendicular to the surface. How's that? That's probably easier way visualization than if you took multi-variable calculus, then this area ds being a vector is no problem. That's how we find it. I'll show you right here. You see ds, we cross the two vectors, these two partial derivatives, and that's really easiest way to find it. But since you're more than a year away from this class, so the way we will visualize it is you take the little area on surface, infinitesimal size area, and then we multiply it by normal vector. Or better yet, this way, right? This times cosine theta is what we mean by dot product. Right? This is like physics definition of dot product. Yes. I can't hear you. Yeah, small tiny little tiles you see here. Now you can see all of these are DAs. And then we add them up. All integral does is add them up, right? We are used to dx's, the tiny little segment on x-axis.
So the total flux is equal to all the sum of all the tiny
things, they are these penetrating thing, except coming out counts as a positive one, and then going in counts as a negative one. Yeah, so that as well. I told you this is confusing, right? Yes. dA is area of this one of the window times the normal vector. Okay, forget it. dA is this window, and then we attach cosine theta. In case this field, you know that in our calculation, these field lines and our displacement does not, in calculation of work, does not necessarily add up. So we have to put f dot dx. You know what I'm saying? That dot product. The work is f dot dx. You know what I'm saying? Or dr, really. So that idea. But how can this be a vector? Well, tiny infinitesimal length, but then you just make it a vector. You know what I'm saying? So all we are doing is tiny infinitesimal parallelogram, and then you just multiply it by a vector. You get it? Are you confused yet?
I think this part will make more sense next.
Right. And this is why this is confusing. Okay? Now, are you ready for a trick to bypass all of this? Yes. I think you've been ready for a while. Okay. So if we are calculating total flux through, let's say, surface 3, which is going to be crazy integral, but that's the same thing as this one. So let's just do this. You know what I'm saying? So let's see what this thing is. S1 E dot dA. Okay? Now, let's just think about this. We know what electric field is, right? Electric field in this case for S1, on S1, electric field has to be KQ over R squared. Eh? We figured that out earlier and last unit as well. And then that radius is constant now, isn't it? On this surface. So this whole thing is constant. Constant is a very nice thing as an integrand, isn't it? Because you can take it outside. The other added nice thing is dot product. What happens to that dot product? Okay, let's just write it like this. This is S1, E dA cosine theta. Let's put cosine theta inside, right? Uh-oh, this does not want to erase. Oh, yeah. E cosine theta dA. So in order to avoid your confusion, let's just insert cosine theta. What is the angle? They're all 90 degrees because if you have a circular, if you have a point charge at the center of the sphere, then the field lines will penetrate the sphere at perpendicular. Meaning, this is 1, eh? Whoa, what just happened? E is constant and our dot product disappeared. Right? So what we get is we can take this thing outside. We have this. Now guess what that integral is? Let's see how much intuition you have. Analogy here is, we'll come back, say we have integral is usually area underneath this thing, right? A to A dot, right? So f of x dx A to B is that area. But what happens if our function is constant? Then it is, we'll just call it C, right? Then it's C, and then A to B dx, isn't it? Is it the same as C times B minus A? Also known as this length, right? It's area of a rectangle after all, so the height times. Come back here. Intuition tells you this is E times what? E times the A. What is our A then? Remember our surface is sphere. You get it? Hopefully you remember area of the surface area of the sphere, or you can integrate and find out. But it's 4 pi r squared, right? So far, so good.
What's the symbol? What's the difference between that and the regular symbol?
Oh, we reserve this circle for enclosed surfaces, not the umbrella-looking thingy, but sphere, football, anything that has inside and outside.
What's that called?
I have no idea. Circular, no. Double integral is in an enclosed surface. And then later in single variable, there's also called a line integral. See, so far we've been integrating along the either x-axis, this is dx right here, or dy right here, right? But we can actually integrate along any curve C, and that's called dr. You know what I'm saying? So in case this curve happens to be like that, then we also use this symbol.
Oh,
Right? It's for that curve.
so there's no real start or stop time.
No, there's no beginning, there's no end. You come back to the same place, is all it means. But then we can extend this idea to surface. That's why it's really a double integral. And yeah, it has to be. Okay, I know, I know, I'm so sorry. This is like chapter 17 of multivariable calculus, and even they haven't learned it yet. In the meanwhile, you have to prepare for AP exam in the self-study. It is what it is. Remember this E? We plug it in here now. And let's see what that gives us. Okay? So we have KQ over R squared times 4 pi R squared. Oh God, hallelujah, R squared cancels, right? 4 pi K Q. You know what I'm saying? I mean, it's not a big surprise, right? Because this is electric field and you're multiplying by R squared, so R squared cancel. And in this unit, you will see this language a lot. This just means it's just different constant. And it has some physical meaning, so, but for us, it's just constant. Or easier way to remember it is this, right? 4 pi k.
What is E0 anyway?
Forgot. It's the permissivity of some, so it is some physical constant. But then so is Coulomb's constant. You know what I'm saying? So Coulomb's constant times 4 pi. And then 4 pi is really a surface area of a unit sphere, if you think about it. And that 4 pi is actually a big deal in higher level math, right? Because eventually in higher level math, this does not need to be a three-dimensional sphere. They call it a ball, some n-dimensional hyperball, hypersphere. Okay, you're not gonna hear about that again until you at least go into upper division in college, so let's not even go there, okay? The whole idea is this. Let's put a summary. Summary is this. The flux count. And this charge, this is enclosed. That's the key. Right? And this is Gauss's law. Yes.
So when we're doing this, is it always like a sphere? Can we use like if we're doing like rod, use like a cylinder or something?
it, see this sphere that we took, S1, is known as Gaussian sphere. We get to choose according to our application, and we have to choose it in a smart way that this always happens. Angle is perpendicular to the field, and the field itself is constant. And by the way, now you can calculate the total flux. You just take the enclosed charge inside your sphere. That's why it has to be enclosed inside and divide by or multiply 4 pi k. Nobody cares about this flux count. Whole point of this was to get this relationship, and we use this relationship to calculate electric field. Okay, yes. Yes, that's the whole thing. If the charge is outside, then it doesn't matter. Remember, this picture is key. Let's say we have a charge somewhere here so that we create that kind of field lines. Total flux count here for that surface is 0. It only cares about charge inside. You get it? In order to have a net positive count. Yes? We will look at that very example. Okay? Okay. So we'll just do this one more time to see if we get the same thing as a point charge. Okay? I guess this we'll have to save it for next time. Okay. Say there is point charge, right? The way you want to do this is you imagine Gaussian surface. In this case, you definitely want spherical. And then you want that distance is r units away, right? Watch this. This is only thing you need to remember. And remember, this is constant and perpendicular at the same time. So what happens is this. Good. And then electric field, and this is 4 pi r squared, correct? And then remember 1 over epsilon is 4 pi k. You usually leave your answer in terms of epsilon naught, but just to prove a point. And then you have q, correct? Divide both sides by 4 pi r squared. Then you have E is equal to kq over r squared. We get the same answer back. And this is not surprising because we use this fact to derive this. Okay? But remember infinitely long wire? Let's do that one. We'll do this example, I guess, next time. And then we'll just do infinitely long wire. Okay? Does anybody remember the answer, or should we go up and copy it?
KQ over R.
What was it?
Is it KQ over R?
Yeah, but my first.
2 KQ over R.
2k, huh? 2k lambda over x. In this case, then it will be r, right? So, and it was ugly integral, right? So let's do the same thing and see if we get the answer, and if so, how fast. Okay? Infinitely long positively charged wire with charge density lambda. Good? Okay, let's see. The Gaussian surface we are going to choose in this case is cylindrical, radius r away, and the length of L. And possibly you're concerned about this L. That's going to mess us up, right? Watch this. We don't have to really write this, but it looks so cool. It's equal to Q inside, right? Over epsilon. Good? Okay, let's start substituting. This surface integral really is, integrals do break up and add, right? So this lateral, let's use capital L because lowercase. You know, I no longer put circle here. You know what I'm saying? Plus 1 from the top the top surface, because that is a surface, plus the bottom. So far with me? While we are at it, somebody tell me what the total charge inside the surface is. Is it lambda times L? Density times length gives you the total charge? Because only the one that is inside counts, right? So the total charge in here, that is lambda L, isn't it? You see? Okay, let's see. Then we'll figure out this dot product. Do you see this is 0? Hence, this is 0. Why is that? Because the normal vector sticks upward here, right? And then field only comes parallel, sideways. There's no vertical field here. Because once again, if you have this field, then that's going to cancel out by another charge in infinitely long wire. So there's no penetration here. Mathematically, the dot product, cosine 90 gives you 0. Physically, there's no electric field in up or down, vertical direction. So it does not give you any penetration here. So that flux count is 0. Does that make sense to you? So we only have this first one here. And here, the angle is 90 degrees, isn't it? They line up. So this, once again, and this E is constant because it's same distance away from the wire, isn't it? So this thing becomes E constant that we are trying to calculate, right? And then dA, everything else is 0, and then you have lambda L over epsilon naught. With me? Okay. Somebody tell me what the lateral area of cylinder is?
2 pi RL.
2 pi RL. And then this one, remember, was 4 pi K, right? Say yes. Divide both sides by 2 pi RL. You see L cancels. 2 pi cancels. K lambda over R. How do you like it? Ain't this convenient? Not only is a lot less work, but less confusing to figure, because we are replacing integral with geometry. And then this looks so much cooler. Right? We'll do infinitely large sheet and we'll call it a day. Yes. Oh, it's in terms of lambda. Remember, lambda is total charge divided by your total length. But this is infinitely long wire, so you do not, then we have infinite charge. But in case it's not infinite, you know what I'm saying? Okay, that L is there, so we'll just put capital L. Okay, so this case, eh? So we have density, charge density of sigma here, right? The way we want to put Gaussian surface is cylindrical, sideways. Good? That's our Gaussian surface. So once again, we write this cool looking thingy. Charge inside, that's the key. Okay, this breaks up into 3 different integrals, right? This thingy, oh, the circle, left, right, left, E dot dA plus the right circle, E dot dA plus the lateral area, right? Oh my God. L and R was a bad choice because lateral. Somebody give me the better name for these things. Okay, side. How's that? It's lateral left, right. You know what I'm saying. You get the idea. E dot dA. Let's look at this lateral first. You know that unit vector comes out perpendicular like that, right? Which is perpendicular to the field, because remember, infinite sheet field goes out perpendicular in parallel. So there's no penetration here, or mathematically dot product is 0. So in this case, this thing turns out to be 0. You get it? So we knocked one integral out. Okay, then let's think about these two. In this set and the other end is this thingy. Did they put it exactly here? Out there? I always like putting it out there. You know what I'm saying? It doesn't. It's not gonna matter. Yes.
Okay, why is only one of
Huh?
like when you split it and only the left piece is circle?
No. This Gaussian surface. Half.
When you split it
Uh-huh.
into the different ones, then only left has the circle on the.
Oh, we are not supposed to have circle in any, right? So two circles and the lateral area. Yes.
When it's closed on all sides.
So it can't be a circle in 2D, right?
No. It has to be 3D only and enclosed surface. That's the requirement for Gaussian surface. So this one has the left, right, and then lateral. You know what I'm saying? And then this lateral integral gives you 0. Okay, let's think about this thing. This is constant, right? So what we have is E outside, good, plus this is constant, and then none of them is negative because it lines up. Our normal here lines up this way, and the other side lines up that way. You know what I'm saying? So they are both positive count. It's coming out of the surface. So this is E. Oh, and then the other side, Q over epsilon naught, right? So far, so good? And then, what is this? Area of that circle. Oh my God. Pi r squared. And then you have another E, pi r squared. And then 1 over epsilon was, remember, 4 pi k. So far, so good? Wait. No. We have to calculate what Q is. So let's calculate the amount of charge inside. Amount of charge right there. Would that be sigma times area of that circle? Would that be pi r squared? Oh my God. So far, so good? Yes. Huh? Yeah. My usual mistake. 4 pi sigma k, another pi r squared. Good. Divide both sides by 2 pi r squared. Okay? So your electric field is equal to 2 pi sigma k. Good. Was that our answer before? In our integral?
So why did you get to this?
Okay, hold on. Let me look up the answer and then I'll answer that question. This one. Right, 2 pi. Dang, huh? So, you got it? So it gives you exactly same answer in so much less work. It's just basically geometry. Oh, not that. Well, this. Basically geometry, but this geometry looks infinitely cooler than any geometry I've ever seen. Because we are still using the language of multivariable calculus. Yes? Yeah, sure. I just wanted to break it out in terms of, number one, it looks cooler, And number two, whoever's watching this video later and looking at these notes, it's that much more clear. So I decided to take extra time here. Yes.
How do you know this with the right side or the left side of the zero?
Huh?
Like, where did you get that part?
This charge inside. Right? So inside, whatever amount of charge you need to calculate that is inside your own Gaussian sphere, Gaussian surface. Right? The way you choose your Gaussian surface once again is your field is either perpendicular or parallel to the surface, right? So that your dot product is either 1 or 0. And then your field is constant at that surface that it penetrates. Do you have any other questions? Alrighty then, I guess we'll call it a day. We didn't get to this very complicated example, but we'll do it on the second unit. I mean, second recording with whatever is left in that unit. Okay.